now recording. Okay, so as I mentioned, let me just admit a few more colleagues that want to join. Okay, so as I mentioned, this project was funded by the Portuguese Science Foundation. The Portuguese Science Foundation in 2007 granted around 234,000 euros to do a work that was focusing on trying to assess a challenge, a scientific challenge regarding the retrieving information from past tsunamis onshore and offshore. So with this challenge, we organized a project that involved a large group of institutions, Portuguese ones like the University of Lisbon, Coimbra University as well, the Instituto Hidrográfico from the Portuguese Navy, University of the Algarve, from the USGS. I'm going to kindly ask you for someone that has the... Okay, sorry. So, so besides the help and guidance in many aspects from the USGS regarding in specific the numerical modeling, we also have the participation from the University of the Rio de Janeiro state that also collaborated on that task. And then we have well, I would say very relevant and very important and crucial collaboration with the German colleagues from Aachen University. And finally, as the end users, we had the Portuguese Environmental Agency. So the project, I can summarize it and be here for a few minutes, but I'll try to, and I hope you can see the video. Let me just make a small correction here. And the video will briefly describe the project. So I invite you to listen to the video. Sorry. I think you can have an idea of the project by looking at the videos. You can still look for it on our YouTube channel and on Twitter. But going to science and the more relevant aspects that we are trying to focus, we are trying to test if the shallow offshore area was really a good archive for tsunami events. That was, I would say, the main goal of this scientific project. We have faced many obstacles when we are trying to look for onshore archives, mainly because of anthropogenic activity and also by the different depositional conditions that make the preservation of deposits more difficult in the onshore domain. So we thought that if we were going to look for the shallow offshore, beyond closure depth, beyond storm wave base, there would be a possibility that some of the events, some of these big tsunami events could potentially be better preserved. Of course, that would imply that we have to look at backwash imprints and couple that with the inundation phase of a tsunami event, that would force to develop as much as we could hydrodynamic and morphodynamic models, if not develop, at least apply the state-of-the-art models that would be available. With this, we were aiming in the long term, let's say, a very ambitious aim would be to develop a more complete tsunami sedimentation model that would involve both onshore and offshore, and the signatures that would be left after tsunami events. Of course, tsunami and tsunami deposits in particular are quite site-specific. They are quite constrained by the site areas that we are looking at. So it's always going to be difficult to apply a global model. Anyhow, we had this aim, very ambitious one, and it's something that we are still working on. We will later mention a few aspects regarding this. This is the team from the different institutions. There's a few names that later join, like Martin Romer from the modeling group. There are other colleagues from Coimbra University that also join at the later stage of the project. But here you have some of the names of the colleagues that participated. The project has 7 tasks, and here we will present results mainly on the tasks 2, 3, 4, and 5, that are the ones that are more relevant in terms of results. But of course, this structure implied that we gathered a large group of experts that had different perspectives to look at tsunami events, with the main goal of retrieving information from sediments to fully reconstruct the events. We are more interested not only in identifying tsunami events, but trying to understand the physical parameters that happened and the physical aspects that happened during those tsunami events, both in terms of hydrodynamics, but especially in terms of morphodynamics. So we looked at the onshore depositional record, and I'll present that in a couple of minutes. Then we also look at the erosional record, mainly the erosion that was caused over the dune fields or the barriers when the tsunami waves overtopped those environments, and then later deposited further onshore a layer of sand or a layer of mud corresponding to that signed the tsunami event. Then the offshore depositional record, and that was particular fascinating for me, and I was really glad with the results that we got with the offshore results and the offshore approach that we followed. Then on task 5, we tried to apply hydrodynamic modeling and also some sediment transport modeling, and later on the third phase or the third module of this seminar, we will present some of the results that we obtained so far. And of course, we always have, we're very keen in integrating all this data. It's a process, it's an ongoing process in research, and we are still integrating results, and I'm sure we will continue to integrate results for the next couple of years or even more. Outreach or dissemination was a very important aspect of this project. I will later mention just a few main aspects that I think should be stressed regarding the outreach campaigns and dissemination campaigns that we used. For those of you that are not so used to the application of the geological archive as a trusted guide of past events, I try to explain here that basically we use the geological record because it will allow us to have a wider window of observation in terms of time. And that is crucial, and it's the only science that allows us that. We need to use geology if we want to study areas like the Atlantic, where fortunately tsunami events are not so frequent. There are other sciences that can study tsunamis, but they are more constrained in terms of the time interval that they can study. especially when we think about the instrumental record, we'll always be talking about less than 100 years. So it's important to always provide and always get our hands dirty and go to the field and search for evidences, sedimentological evidences of these past events. And the idea is also to be able to better predict possible future events. So if we understand better the past, we will be better prepared for the future. It's a common wording of geosciences. Within this project, we're able to continue the tsunami deposits database that is available online. It's growing. It's never updated enough, but it has two options of display. One is the map view, where you can click on Google Earth or Google Maps and look at the different locations where tsunami deposits have been described in the Atlantic. We are extending this to the South Atlantic as well. And you have the table view where you can search not only for the specific locations of each site, but also to information regarding characteristics of the deposits, distance inland where the deposit was found, proxies that were applied, age of the event, generation mechanism, and of course, important references, or at least selected references for each one of the locations. So this was something that we are proud, and it's always incomplete as any database, but we will try to make an effort to continue updating this database. Again, I would like to stress that we are commonly, or over the last, I would say, 20 years or something, when tsunami deposits or this field of science grew up immensely, especially after 2004 and 2011, we focus essentially on onshore deposits. Later on, sorry, just adding 3 more people. Later on, people start realizing that we are having an incomplete picture of the whole event. If we look at the initial papers from Atwater in 87 or Dawson and others in 88, they were essentially interested in identifying deposits. That evolved a little bit and evolved immensely after 2004, when we passed from the pure identification to trying to reconstruct, to try to see if each grain could tell us a story and we could be able to detail what happened. So that led us to look beyond the onshore domain and starting looking at the shallow offshore, as I mentioned. If we go to the deeper offshore, the probabilities of having a nice preserved deposit with a terrigenous imprint will decrease immensely. We can have turbidites or we can have similar deposits, but to have this mixture only in a very specific spatial terrain, spatial domain will happen. At least that's what our results show so far. And I think this was one of the motives that we were also trying to look at the shallow offshore. Of course, many of you are aware that it's not because we have a sand layer that we can say it's a tsunami layer. We do it the other way around. We have to discard all the other possibilities. And for that, we have to go through all these different parameters. We look at the peculiarity of the event. We look at compositional differences, textural differences, paleontological characteristics comparing with the under and overlying layer. The same for geochemistry. We look at the larger scale of geomorphology, where we can see sometimes in dune barriers, we can see the overtopping being imprinted geomorphologically. And we can also use geophysics to try to map specific layers. On top of this, and we have to go through all these proxies before we ascribe a layer as a tsunami layer, or at least as many as possible, we try to go through them. We always have a problem of dating tsunami deposits. They incorporate all the material. So we try to date the over and underlying layer, and sometimes we try to date the layer using OSL or other proxies. So why is the Portuguese case study so important? Well, As you can see on the left image, a paper from Duarte and others from 2013, it has a nice map of the structures that are involved in this area. There's been discussion since the 70s about the initiation of subduction in this area. This has been recovered more recently about this theory. So that is an area of particular interest in terms of geodynamics, in terms of tectonics, and essentially because we still really don't know where was the epicentral area of 1755. We cannot pinpoint the area. We have different possibilities for that big earthquake and that caused this huge tsunami, but there's still a lot of doubts. And this has been studied, and I brought here a paper from 92, when the first studies after César Andrade's PhD in 91, there were a couple of papers that followed during the 90s. And that's always been an event that intrigued the scientific community. 1755 is something of like a mythical character. So it would be important to study this to really understand. And one approach would be to study tsunamis, as it's been used in the past, like using back ray tracing from tsunami travel time. Maybe we could also use tsunami imprints to try to constrain the epicentral area. This has continued from 92, and we have here a recent paper from 2021, also part of OnOff, with a group of colleagues, where we try to review the onshore imprints of tsunami deposits. Of course, some challenges, and a special issue was published on sedimentology, and we pinpointed some challenges that we thought were going to be the near future of tsunami geosciences. So we mentioned offshore, the internal structure of the deposits with increasing higher resolution. We mentioned the problems with age estimation, numerical modeling, empirical tests, and others. And on this OnOff project, we try to address the ones that are in yellow, and hopefully on the follow-up projects, we will continue looking at age estimation and empirical tests. Empirical tests, I think, will go ahead with the help of the German colleagues. And there will be other steps that will happen after OnOff, but I think these three main aspects, we started addressing them, but there are many questions, and that's good because it keeps us with a job. Basically, it's good to have questions because that keep us focused and keep us with a job. This is a conceptual model drawn by Lisa Feist. She will probably mention it later today. That essentially explains the area where you can have potentially you can find some deposits on the shallow offshore area. This will be explained later on this seminar, but it's just to stress that we are talking about a very specific depth intervals where you can find this type of deposits. So this would be the initial part of my presentation. I'm now going to change to another one, so I'll just stop sharing this one, and I will appreciate your help and patience. And I will now change to the second one, which I'll try to be quicker presenting this. Let's see if you can. Sorry. Okay. Let's see. Sorry. Technical problem. Sorry for this. Can you see my presentation? No.
Yes.
Okay, thank you. Okay. So regarding the Portuguese onshore record, Professor César Andrade here in the middle, he was the one that kickstarted the search for tsunami deposits. This photo, both on the left and on the right with Francisco Fatela hammering what we call a box score in the wall of a trench. These photos are from 2007, when we had a project called GETS that helped searching for more locations where we could see tsunami deposits in Portugal. On the left image, on the left map, you can see locations where tsunami deposits have been described. They have been essentially ascribed to 1755, although there's a couple of older events, especially related with boulder deposits in the Cascais, Cabo Raso area, and also in the Praia do Malhão in the southwestern coast of Portugal. The geomorphological imprints that we were able to see, this is in central Algarve, this geomorphological profile. And basically what we saw, and I hope you can see the mouse, there's on just next to the inlet that you see on the left, on the western part of the image, there's a small dotted area that you can see, and that is a fan. It's a fan that was pushed inland by the tsunami waves. We later dated this with OSL, and we got an age that was compatible with 1755. So basically we have a dune field here, and then part of that dune field was pushed inland. We have a depression just to the east of the estuary, the small estuary that you can see on the western sector of the image, and a fan that was produced because of the erosion. And this was dated with 1755. It's funny that when we look at other locations worldwide, we don't see such a slow recovery like we see here in Portugal regarding these coastal systems. When we compare with Indonesia and other countries, we detected that the Portuguese coastal area, especially in southwestern Algarve, in the southwesternmost part of Europe, is very slow to recover. So we can still see some geomorphological imprints, and that is essentially due because it's a sediment-starved area. And that, in a way, facilitates our work because it still has some geomorphological evidence. Typically, the geomorphological evidences that we see here are essentially sandy layers that are over and underlaid by mud deposits. So we typically went to estuaries, coastal lagoons, alluvial plains, and in those areas we were able to detect, usually around half a meter below surface, we were able to see a sandy layer. Sorry, just mute. So we were able to see a sandy layer that thins and finds inland, has an erosional contact, and has many of the characteristics that we usually see with tsunami deposits. There are many peculiar aspects that we will be able to discuss later on, but these are some of the more common aspects of the tsunami deposits in Portugal. We were able to constrain the height of the tsunami waves by looking at how the thickness of deposit varied. So we assume a central axis with the variation of the thickness of the deposit, and then pinpoints that axis will pinpoint to a coastal area, to a specific area that is the entrance from the waves. In the case of Salgados, you can see under the black dashed lines on the central image, you can see the area where the waves overtopped, and they were not able to overtop the other areas, and that's why the thickness varies along, the thickness of the deposit varies along that direction. One of the aspects that we always try to do was, as I mentioned, the aspect that you have on the left is 30 centimeters of sand. It has mud below and mud on top, and apparently it's really hard to see any differences. But in fact, when we increase the resolution, in some cases sampling every half centimeter, we were able to detect variations in terms of composition. The example of rounded zircon and neohedral zircon, one indicating backwash and the other one the eudral one indicating inundation. Sorry, the eudral one indicating backwash and the rhodant one indicating inundation phases. Also in terms of foraminifera variations, also in terms of microtextures in quartz grains, etc., and geochemical variations, we were able to more or less perceive that there were three main phases for the 1755 tsunami event and then a recovery phase. And that was due when we increased the resolution and we look at all these different analyses. So during OnOff, we revisit some of the sites in collaboration, for instance, here with some Polish colleagues and the project that they are currently doing, also including one of the Portuguese locations, Martinhal, in the extreme southernmost area of Portugal. We dug a very huge trench, one that every geologist dreams to dig, because it was quite wide and we were able to see variations in the thickness, variations in the microtopography of the tsunami. It's hard to see, I don't know if you see my mouse, but to the left of, I think it's Robert Jagodzinski in the blue t-shirt, to the left you can see some yellow lines that are the sandy deposit, and it varies, and we were able to see that with high detail. The deposit varies a lot, and when we go further to the coast, on the left image it's closer to the coast, the top is essentially sand, and the deposit is somehow in the middle of mud, so it's quite complicated, and we are talking about a trench of, let's say, 70 meters long, and we saw huge variation when we were looking at the tsunami deposit. So this was also of benefit for Project OnOff, revisiting these classical sites like Boca do Rio, Martinhal, Salgados, and so on. Some of the works are continuing. Then we have a new location that is really in central Algarve. Almargem is here. We did 6 trenches that were excavated immediately inside the lagoon. The lagoon was dry. You can see the images here of trench 5 and trench 6. Trench 5 has only sand on the top, 30 something centimeters. Trench 6 has almost a meter of sand. And as you can see on the bottom right image, there's a lot of darker layers, and they are caused by heavy minerals. And this is very important because this trench 6 is the one that is closer to the sea. So it was able to preserve several storm events. And we, in the same location, similar to Martinhal, we can study tsunami and storm deposits. This is just to give you an idea of some of the analysis that we did. There's some preliminary OSL results that also seem to confirm 3 major phases. There's also very nice pictures from the X-ray that you can see all the heavy mineral layers and all the structures that you can see on them. The tsunami deposit is basically just above the mud on trench 6. And then after that, the barrier was destroyed, the system never recovered. So every now and then you have major storms that overtop the now shallower area barrier, and this made it possible to have all these deposits. Finally, on a very recent field campaign, you have here a drone image. It's still work to be done, but it's the easternmost location in Portugal, southeasternmost location in Portugal, where we detected what potentially could be the 1755 tsunami. The depths are consistent with what we've seen in other areas. It's really close to the border with Spain, and it's something that is of relevance for modeling efforts that will continue. Just to finalize this part, and then to pass to Susana Costas, that will present some of the preliminary results that we got from GPR. Just to mention that with the erosion marks that we saw on the dune barriers and that were dated by the 17, that were dated with OSL, we more or less got an age that was corresponding to 1755. So the erosion mark was around 6 meters. And when we look at the depositional mark and the variation of the thickness, it pinpoints to areas around 10 meters. So that means that with the erosional base, with the erosional features, we were able to constrain a minimum height, and with the depositional features, we were able to constrain a maximum height for the tsunami wave. So we are quite confident to say that the physical evidences that are archived in the lithostratigraphy of these areas pinpoint heights around 6 to 10 meters above mean sea level. So now I'm going to pass to Susana Costas, and once Susana finishes, we will open a few minutes for discussions. And once more, I apologize for the long presentation and for the slight delay. So let's see if I can find Susana. Sorry, just a second.
Hello. Hello.
Okay.
You find me.
Yes. Okay, now you can share, and I'll stop sharing.
Okay. Okay. So can you all see the presentation?
Not yet.
No? No. Because I have to tell it to share.
Okay.
Now you can see yourself. Okay. See? Is it working?
Yes, Susanna.
Yes. A ver. Now wait, because this. Okay, I hope you can all see my screen sharing. Okay, so I'll go ahead and talk a bit of what we tried to do in task 3, which was devoted to investigate the onshore erosional signatures. And as Pedro was saying before, we apply the same approach that we use in this paper that we published in 2016. So what we did in this case, we went to Praia Grande in between Salgados Lagoon and Alcantarilla Estuary. So here, this dune system, and we ran several GPR lines across the dune in order to visualize, to get images of the subsurface and to understand the formation of this dune system, and to see if we could have an idea of to which extent also the tsunami impacted the dune. You can all hear me well, right?
Right, we hear you.
Because I don't hear any noises, so it's so...
Everybody is behaving, is listening.
Yeah, they're behaving too well. So the thing is that our idea was to try to do the same, because we found really interesting results here. Here we were identifying the different units within the radar images, and they were all telling us that the most of the dune system was formed by transgressive dunes, meaning that dunes moving inland in the past. In some cases, we were also able to identify some beach deposits on top of which the dune was moving inland. But the most interesting thing for the tsunami point of view was the identification of this surface that was like defining 2 stages in the evolution of the whole system, of the barrier system. And then we we interpret this surface as a discontinuity or a sort of an inundation surface, suggesting that probably part of the system was overtopped by the waves of the tsunami. And then, as Pedro was saying, that the inundation could have reached between 6 and 8 meters in this area. So this surface is not a clear erosive surface in the sense of the inundation, but is like more probably suggested that could have been some inundation, and this inundation would destabilize the Aeolian system and induce some formation of parabolic dunes that are the units in blue. So the latest part of the evolution of the system. And as Pedro was saying, we had these dates suggesting that the blue deposit could have been formed after the tsunami. So with this idea in mind, we had the challenge of finding new places that were fitting the conditions that we had in mind, that were, if we want to find more erosional signatures in the barriers, we have to look for barriers that are high enough in terms of elevation. And as Pedro was saying, we had a lot of too many challenges because of the low preservation capacity, or that is characterizing this coast, as the whole coast is, we could define it as a transgressive coast. So these areas that we are interested in exploring are being dismantling or eroded or disappearing because of the retreat of the coast. No, so we were trying to find these areas. So we crossed the border to Spain and we went to Punta Umbria spit. That we thought it could be interesting because the attached area of the spit to the mainland had a huge area that could be suggesting overwash or sort of an older system. And the present day dune is quite high in elevation. Then we went to Albor estuary because the barrier there is quite wide. And it has some areas with elevations around 7 meters. And so we thought that could be also a candidate. And also we went, of course, to Martignal. Though in Martignal, if we have, some of you have visited the area, the dune area here is Remand. We have very small patches of dune, but this dune is actually also very high. So regarding the results we got in Punta Umbria, they were quite interesting, the results from there. As you can see here in the interpretation of the georadar images, we were able to identify the dune system, but the whole system is showing signs of retreat. So we were a bit concerned that if we do something here in the dune, in the present day dune, probably everything is going to be too young because of these clear signs of retreating of the system. Also, the dune is fragmented in several areas with the formation of blowouts. We can see several parabolic dunes going through the system inland, but this was really interesting because the area, as you can see here, it shows like a layer of sand with very big shells that could be indicative of an event of high energy. And also the GPR is showing this washover deposits that could also suggest the inundation of the system. However, it could be older or younger than the tsunami, so we didn't risk it here. Also, the reconstructions in the area based on historical maps, if they are good enough, or if they have enough data, we don't know. But also they were suggesting that the area of the attach is younger than the tsunami, but this well, it's not clear, and these breaching areas could be related to high energy events like a tsunami, but it was too complicated, so we decided not to drill here or to find samples in the dune, because the actual dune looked quite young. Then in Albor, we had a quite different system. We could see the progression of the system. This is the barrier system is quite wide, and we can see the progression of the beach seawards, like forming small beach ridges that are progressing seaward, and then very close to the shore, the higher fore dune, that is this small ridge here, but the elevation of most of the system is not very much above 7, 6. This, for example, where we were able to run the line, the transit, was only 5 meters. So we were not also very confident that this could give us the results we were aiming for. And finally, the Martignal area is this remain of the dune here. Is a very interesting area because it's a very high dune, not very common here in the Algarve coast. And it's very sad because the whole system is disappearing, and nowadays not only because of the erosion from the waves, but because also the human pressure, because everybody likes to jump from the crest of the dune towards the beach, and that doesn't help to the survival of the dune. No? So in this area, we were able to identify again the beach deposits, and the dune, we saw that there were two main phases of the growth of the dune. One first phase characterized by the typical growth of a fore dune with the aggradation of the system and the progression seawards of the fore slope of the dune. And then a final stage, or the crest, the present day crest, is mainly characterized by a transgressive dune, so the system moving backwards because of the lack of vegetation also in the front of the dune. So to summarize what we have seen in these three areas, in general, the results were very interesting, especially in the Rompido Spitz. But the problem is that the indications we had were not very clear in terms of what we wanted or what we expected. Maybe this area is really interesting in terms of the evolution of the whole system, but we are not sure if the tsunami is imprinted there. Maybe it is on the Overbos area, but that was not the focus of this task, so we were not touching that. And Martignal is very interesting, and it's a pity that maybe it's not gonna last very long, that dune, unless they fence it or they try to avoid people to get into that system. But also we weren't sure that the evolution, that two phases of evolution of this dune would be related to the tsunami, but maybe more something also related to the use of the beach more recently. And that is all from my side. Thank you very much. I pass it to.
Okay, thank you, Susanna, for this. We are slightly late, so I have to be very. I'm a bit concerned about timing, so I'll give just time for a couple of questions. If someone has questions, you can write it on chat, or we can progress to the next presentations that will focus on the offshore. As a summary, I would say that the onshore task, I would say it went well. We managed to study in more detail very well-known areas where tsunami deposits have been extensively studied in the past, and we can still find new things. I forgot to mention one of the most intriguing aspects, and we have been discussing this, is that we usually have assigned a tsunami deposit as exclusively made of sand. And in the case of a place like Boca do Rio, for example, it was always striking that while all over the depositional basins that we are looking at, the deposit was around 1755 deposit was around 50 centimeters below surface, and in Boca do Rio was much lower. We initially thought, and we still think, that that has to do with the tributaries, with the rivers that drain to that basin. But another possibility is that we have neglected the silt deposition associated with the tsunami deposits. And that opens a huge avenue for research that we will pursue in the case of Boca do Rio, in the case of Martinhal. But I would say globally, it's something that should be looked at. So, because when we started, we were so keen and so formatted to look at just look at the sand in the middle of the mud, that we missed what was immediately above the mud. So that also needs to be considered, especially when we run models, when we look at other aspects, other areas. So that is something that was also I'm just going to, so there's a question from Otman asking if there are any ongoing projects like this on the Moroccan coast. I'm aware of a few, and I'm aware of also a few applications. So I don't know the state of the applications, but Morocco is also very interesting, not only for sandy deposit, but also for boulder deposits. There's been a couple of publications. Several Moroccan colleagues have searched extensively, and ourselves on project nearest European project, we spent a few weeks in Morocco searching for tsunami deposits, and it was not easy, but I'm sure there will be, and I'm sure it has an extensive coast that offers a lot of conditions to find this type of deposits. Just to go back and to conclude this part of the onshore, it was also very positive to find new locations. So despite all the effort, we were able to find 2 more locations, and one is of particular interest, the one that is located really close, for those who know, to Monte Gordo, which is the extreme southeasternmost area of the country. And it's of relevance because of its location. And on terms of the erosional signature, it was very good in central Algarve. It was not so successful, as Susanna explained, because of lots of constraints, but it's something that I would strongly recommend that is pursued elsewhere. So if there's no more questions, I'm going to pass to Lisa Feist, and she's going to present. Oh, Francisco, sorry. Do you have a question, Francisco?
I'm just clapping the the former presentation, the presentation of Suzanne and the presentation of you.
Okay, thank you. So I'm now going to pass to Lisa Feist, and she's going to start on the let's say, I don't know, the crown jewels of this project, that is the offshore domain. And so I pass it to Lisa. Thank you all.
Okay, can you hear me now? Yes. Now you can.
Yes.
Okay, I'm trying to share my screen.
Okay.
Okay, you should be able to see my presentation now. Yes, great. Okay, so welcome everybody. I am going to present to you the offshore record of tsunamis, and the major part of it is the RV Meteor Cruise M152. I will start with a general introduction. In November 2018, we set sail with the German research vessel Meteor with the objective of analyzing sedimentary characteristics and paleoecological effects of the 1755 Lisbon tsunami. We had very tight time constraints of only 3 full working days to work on 2 transects perpendicular to the Algarve coast, and these 2 transects were mapped mainly during the night and sampled in water depths between 60 and 800 meters during the day. The following scientific questions were in the focus of expedition M152. First of all, do variations in thickness, sediment composition, and preservation of a 1755 Lisbon tsunami deposit exist on the Portuguese continental shelf and slope? Are preceding events of the 1755 tsunami recorded along the Algarve coast, and can information on timing, frequency, and magnitude of these natural hazards be obtained? And what effects after offshore tsunami backwash deposition can be observed? And ultimately, what are sedimentological characteristics for the identification of historic and prehistoric tsunami deposits on the shelf? To address these scientific questions, we conducted a total of around 400 kilometers of hydroacoustic profiles that were collected during the 3 working days in the study area. Additionally, 4 gravity cores were collected in deeper water depths along the Portimao Canyon, which you can see here. On the Algarve continental shelf, in water depths around or less than 110 meters approximately, 19 sediment cores were retrieved using a Viper corer in an eastern transect here and a western transect here. At some stations, for example, station 19, duplicate and triplicate cores were collected to obtain more sediment and therefore to have more sample material. And also 8 additional grab samples were taken in a transect parallel to the coast and in an extension to the west transect along the continental slope. The retrieved data and cores were and are still addressed in our labs by means of a multi-proxy approach. You will hear more about this later by my other colleagues. And also additionally, the Institute of Hydraulic Engineering and Water Resource Management of Aachen University used water and bottom sediment samples for analysis of microplastic content in the Eastern Atlantic Ocean. Further information and details about the applied methods can be found in the cruise report. You can access it online following this QR code now, or just contact me or Pedro or like one of the colleagues later during the seminar for a link or a copy of the report. So let's continue with the hydroacoustic results. The hydroacoustic survey included sub-bottom profiles to visualize the shallow sedimentary cover of the shelf and to facilitate the recognition of geomorphological sinks, basins, and submarine valleys. These provide high preservation potential of event deposits and therefore serve as the most suitable coring locations for us. So we were looking for these locations. According to the profiles, the study area is generally marked by rough erosional seafloor and frequent exposure of bedrock. For example, here or here, you can see this clearly. The profiles show different penetration depths varying from near zero in areas where bedrock is exposed to a maximum of almost 30 meters in areas with high accumulation rates, mainly found in the before mentioned sinks and basins, or here in the eastern part of the transect in a sedimentary prism. Today, we focus on the western transect, which you can see now. And there we can find a great contrast between fine and coarse-grained units that is noticed in the profiles, but also in the cores. Notably, the profiles from the shelf's shallower part reveal a distinctive strong reflector within the sedimentary cover. This strong reflector indicates a strong contrast in materials, for example, coarser or compacted material intercalated in the homogeneous background material. This reflector can be correlated with the coarse to an event layer that is deriving, or that we interpret as deriving from a tsunami in around 3,400 years ago that I will tell you more about soon. Yeah, these are our rapid cores from the Eastern Transect. And here you can see that different stratigraphical stacking patterns exist because most cores in the Eastern Transect are located in the sedimentary prism that you could briefly see before. This sedimentary prism thins out to the east and to the south. So the cores of the proximal part of the sedimentary prism are placed in a stratigraphically higher position within an aggrading sedimentation regime, while the distal cores are placed in prograding units. Also, the general sedimentation pattern changed over time due to the post-glacial sea level rise. In general, the cores at the isolated basin and the proximal part are dominated by coarser material, while sediments become finer towards the distal part. The low energy environment is interrupted by poorly sorted larger grained unit E1, which you can see marked here. This unit contains large shell fragments indicating high energy conditions. This unit can be found in several other cores as well. So now in the Western Transect, from the subbottom profiles of the Western Transect, it is evident that the area qualifies as a typical sediment-starved shelf. Again, the general sedimentation pattern changed over time as a result of post-glacial sea level rise. You can see this because coarser sediments representing higher energetic conditions are found towards the base of the cores, and finer grained sediments representing low energetic conditions are found towards the top of the cores. The finer grained background sediments are interrupted again by several intercalated coarser grained units that represent episodes of higher energetic conditions. For example, unit E1 or unit E2 or these other small units that we are not so sure of yet. The remarkably strong reflector that you could see in the subbottom profiles corresponds to the sediments of unit E1, which are interpreted as high energy deposits. So we're going to have a closer look now at core 19.1, because this is located where you could see the strong reflector in the subbottom profiles. So here you can see a photo of core 19.1. And based on the applied multi-proxy approach, several characteristics for the high energy units E1 and E2 were identified. I will just briefly show this without detailed explanations because you will hear more about this from my colleagues later. So Annabella and Joao will present this, I'm sure about it, and also Santi and Piero. So unit E1 in core 19.1 can be clearly separated in 4 subunits. It starts with an erosive base here, followed by a shell hash layer. This is followed by inverse grading of fine sand and a muddy matrix, and ultimately by a massive medium sand subunit that is void of any matrix material. This is topped by another erosive contact and some sand grains and shell fragments mixed with a muddy matrix on top. Unit E2 is much thinner and less pronounced as E1. The contacts are hard to exactly identify because they are heavily affected by bioturbation. And in general, unit E2 can be characterized by shell fragments and some larger grains in a muddy matrix, but it's not so well pronounced. Interestingly, some geochemical properties change during and especially after the event, but you will again hear about this later. Based on our age depth model, based on 13 radiocarbon ages, unit E1, as already said before, reveals an age of around 3,400 years BP. This means that this event is yet unknown in Portugal, but it may correlate to onshore tsunami deposits in southern Spain and also Atlantic Morocco. The ages of unit E2 are in agreement with the 17.5 Lisbon tsunami. So in summary, we learned that unit E1 presents a broad longitudinal distribution on the shelf, as it is traceable in some of the subbottom profiles and cores in both the Western and Eastern transects. Based on the sedimentological, granulometric, compositional, and other features, the distinctive unit E1 sharply contrasts with the background sediment of generally calm environments. Common features for all cores are high energy indicators, such as erosive bevel contact, coarser grain size, as well as contrasting geophysical and chemical properties compared to the background sedimentation. The unit shows a diverse appearance depending on location, with distinctive subunits at location 19. And yeah, this specific deposit configuration can only be found at core location 19. So all these features together lead to our interpretation of a tsunami origin for unit E1, displaying complex local transport mechanisms. So in summary, what did we learn from M152? We learned that preservation of tsunami deposits is possible on the Algarve shelf, even though there are some limitations due to, for example, post-depositional bioturbation. We learned that offshore tsunami deposits can only be found at specific locations, and that the observed characteristics are strongly site-specific and can display substantial differences for deposits of the same event in different locations. And these deposits can contain several pronounced subunits related to changes in hydrodynamic conditions and sediment supply. So what does all this mean for tsunami research in Portugal? Our findings complement the Algarve tsunami record with the detection of the sedimentary remains of a 3,400 BP old tsunami. This has not been detected before in Portugal. And also unit E2 correlates well to the prominent 1755 Lisbon tsunami, so we were able to detect this one. And there are several more potential event layers that we identified in the Algarve shelf cores, but these need further investigation to be sure of the event type. So altogether, offshore tsunami research shows great potential to extend the region's tsunami record. And with this, my presentation is almost coming to an end, but I will briefly introduce you our output related to M152 and give you a short outlook into the future. So M152 is part of 4 international publications: a regional study of microplastics in surface waters and deep sea sediments south of the Algarve coast by Simone Lechthaler and colleagues, and environmental changes and cultural transitions in southwestern Iberia during the early Mid-Holocene by Cristina Valpeon and colleagues, and the Mediterranean Sea and Gulf of Cadiz as a natural laboratory for paleotsunami research, recent advancements. Here, 152 is part of the advancements in the offshore sector, obviously. And just as recent as last week, the contemporary pollution of surface sediments from the Algarve shelf Portugal was published by Piero Bellanova and colleagues, from whom you will hear more later today. Also, different topics of the cruise were presented at various international and national conferences. And 1 PhD thesis, as well as 4 Master of Science and 6 Bachelor of Science theses were partly based on samples from 152. But more publications are in preparation and will follow in the future. And hopefully also my PhD thesis will be part of that soon. And we not only have more publications that will follow in the future, but also a lot of results are still in progress. So during the pandemic, we were a bit slowed down, but now we're back on track. And for example, in January, we conducted high resolution CT scans of some of our samples, which you can see a beautiful image here. And these are very promising and interesting first results. And so there's still a lot to do and a lot to look forward to. Yeah, at last, I want to share with you that some of our data, the master tracks, the raw bathymetry, are available at Pangea. And also we acknowledge all efforts and support by the research and technical crew under the command of Captain Hamacher and our chief scientist, Klaus Reicherter. And we are very thankful to our funding partners and all members of the Shipboard Scientific Party and land-based scientists. And with this picture of the Shipboard Scientific Party, I end my presentation today. I thank you very much for your attention. If you have questions, there will be some time for it later, I think. And now I hand over to my colleagues, Annabella and Joao.
Thank you, Lisa. Brilliant. Thank you. So Annabelle and João, if one of you wants to start, we
Hello.
will have time for questions once we finish these offshore presentations. We'll have time for questions. So, but go ahead, João.
Hello to everybody. It's a pleasure to be here to present. I will not present such beautiful results. I'm only focus on the first part on the field work, and then Annabella will do the data integration and so on. May I share my screen?
Yes, I think so. Let me just say that João and Annabella are from the Portuguese Hydrographic Institute, from the Portuguese Navy, and they were essentially for the successful collection of cores with an exceptional vibra core that they use and they have and they produced that should be commended for the results that we got, because it was all due to the vibra core and the exceptional team that was on board with us. Thank you. So João, go ahead.
I don't know if you see me. Okay. So let me. Sorry. Okay. I will talk a little bit about our technique of vibra coring that we used, that we developed about 20 years ago, when we bought the first head, vibra head, and started to improve the system. On the M152 cruise, we used our P5 Horsfelder system that was built by EH. Basically, it's electric vibra core with 5 tons of maximum penetration force at 60 cycles per second. So we have used 6-meter long barrels and with 1.6 millimeters diameter. And the good thing is it has a rigid articulated frame with a 2.5 meters wide base. Why this is very good? Because we developed this system that achieves two advantages. We can articulate it on the deck and take the tubes off, and at the same time we have sure that the system is verticalized and has vertical position on the bottom. Another thing that we also use, it's the transparent liners that gives us the general view of the sediment. And the important thing here, it's a very low thickness of the walls of the tubes and liners. Another aspect is we can measure the barrel penetration. It's a very important thing for us. So the maneuver demands very big cranes and A-frames, because all the structure have about 7 meters long. And needs about 6 to 7 guys to operate on deck, as you can see. But this aspect is very important because you can articulate it and then take the barrels of the vibra core with the very smooth operation, so that we can preserve the conditions of the sample. The thin wall of the tubes turns that the sediment has a very nice contact with the liner, and this is very important for measuring something like the P waves. P waves demand that the contact of the sediment with the walls are good, so the measure can be correct. But the preservation of all of the sample diameter is essential for instance, measuring the the magnetosusceptibility in volume, because you need that the sample maintains all the same volume all over the liner. Those were the vibrocores we made, a total of 21 with repetitions of the 19 that Lisa referred, and the depths were between 1113 to less than 60 meters or 70 meters. One good thing is, since that this system vibrates with small amplitude movements, it penetrates very slowly. So the vibrocore performance, normally it's excellent, because as you can see, the average recovery rate is 92%. You see, the less it's 80 or something like that. Are you hearing me? Okay.
Yeah, yes, sure.
Okay. The biggest, so the biggest score we managed to get, it's 5.38 meters with penetration of 584. It's a recovery rate of 94%. So those are the cores that we got on M152 cruise. Another field campaign was the field where on 2020 on our small vessel we made a sub-bottom profiler on the OnOff project, and also sampling on the SEDMA project. It was two projects on the same cruise. Here we used the parametric NOMAR sub-bottom profiler of Ghent University that we adapted to the vessel. Sorry about the sound. This is the sparkler system on the recovery moment. Okay. And this is the survey lines that were made with the INOMAR and the sparkler system on the 2020 geophysical survey. It's about 900 kilometers or something like that. This was the first moment when the 3.4 thousand years episode appeared when we were doing the F5, as you can see there, F5. It appears at about 62 meters, but we believe by the coring that were made that it could appear on greater depths. Okay. Next to the geophysical survey, we made those stations with the Smith-McIntyre grab. And sorry about the noise. And this is the moment where we are launching this Smith-McIntyre grab. Okay. So we made a total of 19 samples. Some of them were the chisel samples, and others are only superficial samples. So this was the field work of M152 and on SEDMA 2020, OnOff 2020. Now I pass to Annabella. Annabella, do you want to?
Yes, João, please. I want to share my screen. Is better.
Yes.
Okay.
Okay. Okay, it's yours.
Thank you, João. Good afternoon to all. Thank you, Lisa. Thank you, Pedro, for being here. I'm going to present some results obtaining with grain size and Schreis ray diffractions in 4 or 5 cores. 19, 22, 13, 10, and 9, collected during the cruise 152. The study area has been shown before. Okay, it's not missing. Is the Algarve Western Shelf, and the geological formations in coastal areas contains exposed limestones, Mesozoic limestones and marls, and also Miocene beoclastic limestones and sandstones, as we can see here. I'm showing some results that Lisa showed. These are the main cores areas, the 19 and the 22, the 13, 9, and 10. On for contextualization, the core sampling, we can see here a seismic line obtaining by a sub-bottom profile system formed again at university that passed throughout the cores houses 19, 20, 21, and 22. These lines show a well-developed sedimentary column with about 5-6 meters lying over rocky substrate, here very well delineated. During processing, we found some problems, namely the lag between the top of the cores and the location of the bottom of the seismic lines. We tried to correct this, but it was not easy, and it was and this mismatch persists after this, some corrections as tidal heights and also the length corrections. In this seismic line, we see here very well the layer that Lisa shown before. Here is an extract from the line from this previous seismic line. We can see here the delimitation, the mark, the bottom and the upper layer with the different acoustic characteristics. We see also here the core depth here, the core depth adjustments that can we can see that this layer of the core correspond to a sandy layer with 40 centimeters above an erosional base. This layer was interpreted as the 3.7, 3.4 Col BP event, as Lisa told us before. The laboratory analysis that we made for this project comprehends for 576 marine sediment samples. This slide summarizes the laboratory analysis. We processed the cores 9, 10, 19, 13, and 22. Due to the low amount of sediment samples in the lab, the treatment has to be sequential, initiating with grain size, and afterwards we do the mineralogical analysis of the fractions under 63 micron. Here we see some data obtained with the grain sizes for the core 19. In the right side of the slide, we can see the log representation of the sediment classification, followed by the P waves, mean grain size, and grain size curves, and also the silt and sand and clay percentage. What we see here in this in these sequences is a base of a silty sand, followed by sandy silt, cut by a coarse, very coarse sandy layer, formed by median sand layer. Here we see that the curve is represented a unimodal curve, completely different from the surrounding sediments. interpreted as high energetic events related with the 3.4 call BP event. To the top, we see also a finer sandy layer that can also correspond to another high energetic event, this one here, correlated with the 1755 tsunami. But we see here that the sandy layer is completely different from the one here presented for the 3.7 call BP. For the core 22, the sequence is slightly different. In the base, we see fine sand with a decrease. Here are the curve. With fine sand, biogenic fine sand, with a decrease of sand towards the top, with increase of silt percentage. We can identify a more sandy layer here at 0.5 meters here in this area, but we cannot tell this is a high energy event. For core 13, we show also a higher content of sand in the base until the 75 meters here. We have a higher content of sand. And to the top of the core, we also see finer sedimentation to the top. Now I'm going to show some results about fine fraction mineralogy. In terms of fine fraction, in this table, we can see the median results obtained for the 5 cores. What we see here is in this table is the high abundance of carbonates in all the cores, with calcite values higher than 40% here. We identify high values of calcite, but also of calcite, manganese, aragonite, dolomite, and also a dolomite, a very rich iron dolomite, with higher important values associated with core 22 and core 13. Other identified minerals were muscovite, chlorite, kaolinite, quartz, copper feldspar, plagioclase, zircon, pyrite, and pyrite. In the right corner, we see this the ternary diagram with the main mineral groups: silicates, phyllosilicates, and carbonates. And they show an increment of carbonates to the core 9, increase of silicates to the core 13. More to the east, and an increase of phyllosilicates to core 10. In relation to core 19, in terms of mineralogy, in the right corner we see the log and dating. In the left, we have vertical profiles of chlorite, mica, quartz, feldspar, aragonite, and calcite and dolomite. The horizontal lines represent higher contents. The green lines represent higher contents of carbonates. The silicates are represented by gray lines, and phyllosilicates by yellow lines. The core base was dated for around 11,000 years before presence, and we see that the base of the core show a high abundance of carbonates, and that provides answer to the 2.5 meters. We have a great abundance of carbonates. And we have a change of the main mineralogical compositions above this level. Above this level, it was dated as 8.2 thousand years ago, and this change can be interpreted as a change in marine productivity or also in the oceanographic regime. After this level and after sea level stabilizations, we see these pulses of more phyllosilicates or more silicates. But this sedimentation, after the stabilization of the sea level around 6,000 years ago, we see these huge hiatus without fine fractions, and that correspond to the 3.7, 3.4 call BP tsunami. And after this event, we see also again these pulses of terrestrial material represented by these horizontal lines with higher content of silicates or higher contents of phyllosilicates. Core 22 show also a base, a very carbonated base. Here we don't have datings. The core base is also richer in carbonates. This core is important to refer the increment of the ferrodolomite mineral in this layer and in some layers. We can see here in the right this graphic that correlates the biogenic carbonates with the detritic carbonates, and we see that especially in this core 22 we have a higher increase of the detritic carbonates. I think this is important. To the top we see also the same as the core 19, namely pulses of terrestrial material of finer and coarser, possible related with the climatic effects. Higher moscovite and elite and chloride contents may be related to cooler and drier climates. For finalizing the core 13, we see also we have now also without dating. The higher content of carbonates in this core was found in the middle here in silty sands, where a slight increase of biogenic sand here in this component exists here, and also we can see pulses of coarse and terrestrial material to the top. Final considerations. The mineralogy show a carbonated rich sediment related with the prevailing limestones, continental sources, and also marine productivity. The 8.2 coal event can also be detected by mineralogical changes possible related with paleoceanographic regimes and marine productivity changes, also seen by Val and Peon et al. In 2021. After sea level stabilization, the pulses of terrestrial material, finer or coarser, can be related with drier, arid, or cooler periods, or humid and warmer conditions. The retrieved cores show evidence of high energy events, namely the core 19. And now we are preparing some articles and communications, and we intend to present one communication in the 7th Jornadas de Instituto Hidrográfico in June 2022. And I finalize this now. Thank you for all.
Thank you, Novella and João, for your presentation, and also for just showing the potential of the results from these cores, that we can go from maybe tsunamis to flood events in paleo-environmental reconstruction. So there's a lot of potential for follow-up work, and I'm glad to see things progressing. So now I'm going to pass, I don't know if Piero is available now. I know that he had a meeting. Okay, so Piero, okay, thank you. So if you don't mind.
Can you hear me?
Yes, we can.
Okay, perfect. Then give me 1 second and I will share my screen.
No worries.
I thought Santi's is before me, but okay.
Well, maybe I mix it.
No worries.
Sorry,
Oh,
maybe it was my fault. So I didn't look at the program. Sorry.
no worries.
We are
No.
so late. I look at the time and then I just, okay, sorry.
Okay, so you see my presentation, right?
Yes, yes.
Okay, perfect. Then I will jump quickly into the organic geochemistry of the offshore deposits. And first, the question why we would apply organic geochemistry. So our theory was that we not only have the transport of particle materials, so sediments, but also of associated organic material, and with the tsunami inland and also offshore. And then we can just drill with the meteor in the soil and get also organics out. So our aims are that we want to identify the full organic geochemical compound spectrum, and this is a reflection and the differentiation between long-term and short-term environmental changes. So that's one of the aims. The second would be a geochemical reconstruction of the environmental evolution of the Gulf Shelf itself, and the differentiation of tsunami or other event deposits from the background input. And then, of course, the comparison between onshore and offshore geochemical characteristics, especially with the 1755 Lisbon tsunami. And we just recently got a project granted by the German Research Foundation to do further organic geochemical analysis. The methods we use, so we do first in solid liquid extraction via overhead shaking, ASE or ultrathorax. Then we do a fractionation into different fractions with different polarities. So we have the different compounds separated, and then we do a GCMS analysis. And our approach was first to take a look on terrestrial versus marine markers, such as fatty acids or hydrolyzable fatty acids. And they represent a natural input of terrestrial material, but they can also be differentiated to for example, algae material. Another factor could be, or another compound could be analkanes and their specific terrestrial aquatic ratio, because they are typically allophtonous input from terrestrial plant materials, and the tar shows us the relative terrestrial versus marine organic matter input. Another indicator we want to take a further look on are steroids. They can be differentiated also in marine versus terrestrial. And then we take a look on, for example, the C28 and C29 ratio, and aldehydes, which reflect typically vascular land plants. And for example, in a tsunami backwash, we would expect more representation from terrestrial input sources. And also terpenoids, which are also representative for vascular land plants. Another approach could be, for example, anoxic versus oxic conditions, which is, for example, represented by the pristine-ketone ratio. This could be indicating for bloomings. Also, we take a look again on terpenoids, for example, beta-carotene. This is associated with anoxic conditions in lacustrine and marine settings. We also take a look on pyrogenic parameters, which are more anthropogenic. For example, the polycyclic aromatic hydrocarbons, they can be in there from consumption of pyrogenic material or of fossil fuels like coal, tar, wood, oil, etc. But also we can take a look on the use of fossil materials itself through hopanes. They can be released by anthropogenic activities. And then we take a look on anthropogenic natural compounds, such as terpenoids again, for example, from resins or other plant materials, which are specifically used by humans in the past, for example, during the 1755 era. Again, fatty acids can be enriched by natural fats and waxes used, for example, in an abundance of food or livestock breeding or so. And then, of course, we take a look on fecal steroids through anthropogenic farming or the outflush from cities. And just for an example, we take a look on N-alkanes. They have a homologous aliphatic hydrocarbons, and they're ubiquitous in nature. We can differentiate them in shorter N-alkanes and longer N-alkanes, whereas the shorter are more typically for marine and algae, and the longers are typically for higher land plants. And for us, the distribution is of interest, especially the odd versus even predominance, and for example, dominance of C29 is typical for terrestrial, but also the ratios such as the TAR, where we divide different concentrations of different alkyls to one another. Another compound are, for example, fatty acids. They are the most prominent ones are the C16 and C18. They're not dominant in fats, but they are both in terrestrial and aquatic life to be found. And here we can again differentiate between short-chain fatty acids, which are ubiquitous in marine environments, medium-chain ones, which are more in lacustrine environment or in macrophytae, and in long-chain fatty acids, which are typically for terrestrial higher land plants. And here we see also a terrestrial indication by, for example, an even over odd predominance. So we have some preliminary results. We focused for the first work mainly on the core 19.2, and we have finer intervals around the 1755 layer and this older 3.4 kiloyears event layer. And the organic geochemical results for the event layers indicate that we have somewhat of a backwash related terrestrial input, or a higher terrestrial input than we have with the background. And we have also a higher pristine butane ratio, which might signal anoxic conditions as short-term events, as these events might seal off deposits from the underlying strata and from oxygen and light. So there might be a relation. Here we can see our very preliminary results. So, for example, for the very old sandy layer, we see that there are some increasements in the, for example, aldehydes for the terrestrial plants, but also up here where the 1755 layer is probably, we see some enrichments, for example, from PAH, which might be related to fires on land. Yeah, but to get a quick outlook, what's going on and what's to be expected in the future, we want to do the analysis of the full spectrum of the organic geochemical proxies, and we want to do the analysis also on several cores and only one, and so we can get a more lateral correlation. And we want to do a comparison between onshore and offshore archives as well. We do also additional offshore work in Japan at the moment. That's where I have to head very soon to an IODP meeting. So we do not only, so we will get more experience with offshore work hopefully very soon. And yeah, thank you very much for your attention. I hope I stick to the 10 minutes.
Thank you, Pierre. I think you were the first one. Thank you. Before we have time for questions and to finish this part on the offshore work, I think now it would be Santi to present the inorganic geochemistry results. I have to say a very thank you to Santi. He's not officially part of OnOff, but he's a brilliant person, an open mind, and it's always a pleasure to discuss with him science, and I've always learned from him. So I think you all will benefit from this presentation. So thank you, Santi, and thank you for your help here and on board, and the floor is yours. Thank you.
Okay, I'm going to share my, I hope, yeah, here. Well, can you see my screen? Okay, first of all, I have to be grateful to Pedro and all the team of the project for inviting me here, and for many hours of discussion and funny times sometimes. And well, as Pedro said, okay, I'm trying to move here. I don't know what's happened. Okay. I'm Juan Santisteban from Spain, something for everyone, and I'm just going to talk to you a little about inorganic geochemistry in the course, in the offshore course. Most of the things have been said now, but well, I will try to say something. As you have been told, during the meteor cruise, there was a lot of cores in different subbasins. We had a visual exploration of the cores on board. We tried to do our best, but then we had to go deeper and deeper, and for that we have the machines to help us. You know, which is the result with the machines? A lot of numbers to be clean, filtered, manipulated, and worst of all, interpreted. Sorry. Well, the best way is to start just with simple statistics that can reveal you simple direct correlations that can serve to simplify the data structure. Sometimes more complex relations, speaking to you about mixed compositions. If you go further in this analysis, for example, with principal components, okay, sometimes it's a nightmare. You can see the lower part, it's just like a nightmare. But you can find some clear relations between elements. Here, for example, this is a cloud of two cores from the meteor cruise, where you can see that, okay, I saw three main components that are shared, one related to carbonates, one related to quartz and feldspar, and another one related to the phyllosilicates. And I told you about mixed compositions, two groups of compositions. And Annabella has told you about this. One lower part of the cores and one upper part of the cores. And also these three main compositions, the carbonates, the phyllosilicates, and the silicates. So geochemistry is just looking what mineralogy is telling you. So with a higher resolution, because we have the machine going deeper and deeper and cheaper also in time and money. How can we use this knowledge? Well, the first one is what I just have told you, the indirect proxies. So here you can see this record of the core 19 that Annabella has told you before, where you can see how, for example, this, okay, you see my mouse, this phyllosilicate free level is correlated to a low iron content. This quartz rich level comes relevant for the silica, and the carbonate that is dominant at the lower part is represented by an increasing calcium. But also you can see how the gravel, the sand, and the mud fractions are also correlated to these geochemical parameters. So in fact, what you have is the calcium is carbonate, it's a gravel fraction, mainly bioclasts. The quartz is the main fraction for the sand fraction, and the phyllosilicates, chloride and micaelite, are the main fraction for the mud. Yeah. Let's go for this 3.4 layer event a little more in detail. When we see this record, the very same record in chemistry and the grain size, we can establish some baselines that tell you about the background sedimentation that is composed, I told you, by aragonite, calcite, phyllosilicates, quartz, and minor traces of palladium and feldspar. But this level goes beyond these baselines. It's contrasting with the surrounding sediment. At the bottom, we have a sudden increase in bioclast, increasing in calcium in gravel fraction, that is followed by a decrease in the mud fraction. Upon this, we can see how the sand, the silica increases, and the mud, the iron, still is decreasing. The upper part, we reach the highest content in silica and also in sand, and the minimum content in iron and mud. But the calcium, the gravel fraction, is not changing a lot. It's only the bottom part. And in this, oh, sorry, I forgot. Well, yeah, we can see the mineralogical composition. And at the bottom, there was aragonite, calcite, phyllosilicates, quartz, like the background sedimentation. But at this medium part, we have only aragonite, calcite, and quartz. Phyllosilicates disappear, as Annabella told us. And for the upper part, sand starts to decrease and mud another time increases. In another time, we recover the phyllosilicates. Maybe we can interpret this in hydrodynamical terms, because at the bottom, what we have is a reworking and concentration of bioclast. The content in matrix maybe is a result of the dense flow, or maybe I don't know why. I have more questions than answers for that. At the upper part, we have a high input of sand, and the settling of the mud fraction is hindered. I don't know why. Maybe it's hydrodynamics, maybe it's a change in supply. But also what your chemistry tells me, if you look at the silica record, is that I'm not sure if there is one or two sublayers, because the trends are slightly changing. At the top, that you can see that is just 3 centimeters in thickness, suddenly stops the sand input, and the settling, the background settling of the mud returns. So maybe we can convert this mineralogical grain size and geochemical properties into hydrodynamic processes. This could be a nice thing. Another use of the geochemistry, maybe for correlation, because we have seen some trends, we have seen some events, we have seen some correlation of elements. Okay, about trends. One of the first things that everyone thinks when talking about oceanic areas is about sea surface temperature. And in fact, as I will say, okay, the 8.2 cold event could be identified. In fact, you can see with the green line, our record of the manganese iron ratio that can be related to redox conditions. And it fits, well, more or less well with the Cacho et al. Sea surface temperature curve for the Alboran Sea. But when I see more records, for example, those of the Western Iberian Margin, sea surface temperature is very variable. And you can see that for the same period, in some places it's rising, some is going down. So yeah, we can try, but it's not reliable because of their spatial variability. But what is a constant is sea level change. Sea level changes more or less homogeneously for the whole ocean. And we can see here the lower part, sorry, the older part of this record that is richer in calcium and also is related to the lower sea levels. Maybe the lower sea levels means more energetic conditions and more working of coarse material or more living species in the south. While the upper part, the younger part of the cores are in deeper portions, less reworking, and then less content in the gravel fraction in south. Well, let's try to join all this. Here we have the principal component, the first principal component of 2 cores, 19 and 22. The red is 19, where you can see the even layer there. And 22 is in the same transect, the western transect. And this event is not clear, but what is clear is that they follow more or less the same trend. So the event is not there, but we can correlate them. If we add chronological tools, well, then we can go further in depth and try to correlate more and more layers. We can try to do this in the western sector, that is, as Lisa said, an started area, but it's very, it has a very homogeneous stratigraphy. we can identify with the green arrow the 3.4 events, more or less clear there because we have dates. But when we introduce the trends here, we can fix the position in relation to the general trends and try to identify the same level in other curves, allowing us to perform a longer, a wider correlation of this. Yeah, for the Western sector is okay, but the main trouble is that for the Eastern sector, when we analyze the architectural stratigraphy, it has a lot of discontinuities, and we have not many dates from this area. So take care. The correlation must be done, but we need to take into account the stratigraphical architecture of the areas. So just to finish, well, to use the geochemical proxies, we need a good knowledge about the meaning of the proxies. To what are they related? And also use them in together with another proxies, because by themselves can tell us few things or provide us with false information. Main uses, direct proxies, we can use the redox conditions, the salinity, etc. Indirect proxies that we have used, just correlating them to mineralogy, grain size, and also for correlation. Here we have used them to characterize the background of the even sedimentation or the correlation of even layers. And a further use of them is just to increase the resolution of the destructive or the highly demanding sample techniques by using a cheaper and higher resolution technique. And that's not another time. Thank you, and hope to see you another time. That's all.
Okay, thank you, Santi. We have a few minutes now for some questions. I just would like to stress that this geochemical analysis can open another avenue for research, like they did onshore. I don't know if you remember the papers from 2012 after the 2011 event, where, for instance, CTA-GEO detected, and other colleagues, the VTech as well, they discuss that the geochemical signature prolongs and can be detected further onshore. So maybe it will be possible to do the same type of approach for the offshore. There's a question here. Do you think that the deposit of the tsunami dated for 3.4 can be preserved in the North Atlantic coast of Morocco? Well, it would be very, very interesting if it is there. As far as we can say, we were able to trace the deposit not only on the Western Transect, and we have to see that the Western Transect is just opposite to an area where we have the most number and the most studied tsunami deposits in Portugal, and I would dare to say in Europe, Boca do Rio, Martinhal. So just opposite to that offshore, we detected the 1755 and the 3.4. We were able to see the 3.4 not so clearly, but it's still there on the Eastern Transect that is opposite to Central Algarve. So I would say there is a potential for the deposit to be in the Moroccan coast. And I'll just say, sorry to mute you now, and then we can open discussion. So I'll dare to say that it's highly likely, or that at least there's a potential for the deposit of 3.4 to be in the Moroccan coast. It has been described for the Spanish coast, but it's the first time for the Portuguese coast that this deposit is there. If we look carefully at the geological and historical records, there's been a lot of discussion in terms of the number of events. What civil protection and the society wants to know is when, how many, and how big. And for that, we need to establish return periods. And this 3.4 will change the perspective in terms of return periods, at least for the Portuguese coast. And if you look at the Spanish coast, there's a lot of discussion going on the number of tsunami events. You can have a few local, you can have some that have overlapping ages when we recalibrate using the new radiocarbon calibrating curves. So I would say that if we have like these two larger events, that would be substantial. And in a way to prove this, it would be good as for science if it's also detected in Morocco. So
yeah, maybe that's also a part to add and stress that we used for the calibration, the most recent curve, the Marine 2020. But if you compare that to older publications, of course, you also have to recalibrate the ages because they are not calibrated with the most recent one.
I just would like to stress one thing, that in a way similar to onshore, where we have to look for specific areas, here there's specific geomorphological settings that make or that increase the potential to find a tsunami deposit. So on the offshore, small basins were the areas where we were able to see thicker sediment, a thicker sediment column, and of course a better preservation of event layers. As I said, this is an ongoing project, and there's been tons of data that was collected. We are not discussing all the data that was produced, but it's encouraging for us to discuss this 3.4 because at least it will change the perspective in terms of return period for the Iberian Peninsula. There's tons of questions that can be raised, for instance, and I'm going to get ahead of myself. So the 3.4 was found in Spain. In Spain, there's a couple of locations where they found the 3.4. I was just going to raise a question that we don't have an answer, is why the 3.4 is so thick compared with the 1755. So we have sedimentological theories about this that we can speculate on. Why not in Portugal? Ask. Well, basically because the barriers. So let me put it like this. So you have the sea level curve stabilizing after 5,000, but the barriers were not fully formed, I would say, until 3,000 something. So we had like RIA systems. So it was the inundations from sea, well, let's say extreme marine events were much more common. So it was much more difficult to see because you would have sand in sand and not the sedimentological contrast when you have the barriers and the lagoonals were, the lagoonal areas were formed. On top of that, I have to say that, and I remember that once with Pedro Cunha, we were in a trench in Alcantarilla, and he mentioned that over there's some coarse layer. And at the time we thought, no, it's just an old beach or something. So if we could go back and look at those trenches, although it was sand in sand and it was difficult to distinguish, maybe those coarser layers that we saw and that we draw and that we disregard because we thought it was just a beach or whatever, we should revisit them. So that is the reason. So as a geomorphological reason, and there's a gap in knowledge. At the time we were focusing on 1755 and we always assumed there was nothing. Sand in sand, it was too difficult to distinguish without the sedimentological of the thickness. Expect thickness of I don't know. So I have no idea what will be the thickness of this layer. I hope my son or my daughter decides to study geology and can find the solution for that. That's probably not for me. I don't know. It's something that intrigues me. It's why is so thick offshore compared with the 1755, and among the on-off participants we have discussed this, and we have no final solution for this question. We are open to suggestions, but it's quite intriguing. One hypothesis had to do with the paleo dunes that were or can be observed at 30 to 40 meters deep, and that they were the main source of the 3.4. So they were totally, or I would say mostly, eroded by the 3.4. So there was not that much sand to redistribute on the 1755. But we need time to prove that, and we need some provenance analysis that we hopefully will conduct in the near future. I know that we are very late, so I'll give time just for one question before I pass to Francisco, my dearest friend from Brazil. I think it's good morning for you. So if there's any other question, we will save it for later. If not, I'll pass it to Francisco. And I thank him for being here to present some of the modeling work. So now we will pass to the modeling work with Francisco, Ivana, and Martin. Okay, so thanks, Pierre. So
hey,
just
hello, everyone.
sorry, Francisco. There was just one question about the depth. So let me, if it's possible to estimate the depth of these sediments in Morocco. If I knew, I would apply to some ship time and I would go. I would say that has to be beyond, so it has to be deeper than storm wave base. In Morocco, I would say that it would be similar to Portugal, so we would always be talking about 15, 20 meters, more than 50, 20 meters deep. And if it's also, let's say, I wouldn't say flat, but with a not substantial slope degree, then I would say that I would focus between 30 meters deep to 150, 200 meters deep. But this is pure speculation. So I have no data about the Morocco shallow platform. So sorry, and now I'll pass it to Francisco. Thank you, Francisco.
Okay, Pedro. My screen is sharing now. Can you see? Okay. Here is 1 p.m. afternoon. In Santa Cruz, California, maybe it's a little early. Hello, everyone. My name is Francisco Dourado. I'm from University of Rio de Janeiro State in Brazil. First of all, I would like to thank to Guy Galfenbach for receiving me at the USGS Pacific Coastal and Marine Science Center in Santa Cruz, California, to perform this modeling. And thanks to Shampoo to host me and teach me how to run this simulation and solve some problems. Many thanks, Shampoo. Without you, maybe this will be too harder. I'd like to thanks to the Fulbright Commission for the grant to be there. Professor Pedro Costa to invite me to participate in this project. I learned a lot of the. Okay, let's go. Our objective in this work was to use the mathematical simulations to try to identify possible sources for a 1755 Lisbon tsunami. To reach this objective, we compare the historical records and geological registers to the results of our simulations. We tested the 7 potential sources for the 1755 event. Some of them are based on bibliography, and the other was based on combination of them. The CTA-GEO was a Cadiz edge, the HSF, the Horseshore fault, the other one Marquês Pombal fault, Gorriga Banks, and the scenario 1 was a combination between the Cadiz edge and the Horseshore fault. The other 2 was the we tried to simulate one deeper structure below the Gorriga Bank and the Horseshore fault to attest. This test was one idea from the talks with Pedro Cunha and the other colleagues. And to perform this simulation, we used the software Delphi 3D Flow. A moment. We tried to test some hydrodynamic tests. What kind of the tests we tried? In a hydrodynamic tests, we compared the tsunami travel time and the run-up history records with our modeled results. As you can see in this table, in red was results that diverge a lot from the historical records. In green is these results that match with this historical data. We put here one virtual tide gauge to test other parameters like I will show a video with some results of this dynamic tests. This is for Cadiz. I'm sorry, I don't know why this video is not playing, but let's do next test. In this test, we simulated the arrival time interval between the waves and the maximum, minimal amplitude and the major wave for our area of interest, comparing with the historical results. I will not fixing this table. In the finish, we can explain better the results. For our sediment transport tests, we tested the simulation results to erosion deposition thickness found in Salgado's site. In this case, we simulated the erosion and the deposition thickness using the same value for a ruggedness coefficient and compare the different sources. Here we can see that the Cadiz source is very, very powerful. And when we compare with Gorrigues Bank and the scenario 2 and 3 is very weak. We can see a video. Let's with the simulation. In red is the erosion and the blue the deposition. And we compare these results with the on-site data. When we compare, we take the better results comparing this simulation with the site collection. Here we compare the same simulation with two profiles where we have some results from the GPR analysis. In black is the topographic profile, and red is the GPR layer, and we compare our results with the both profiles, profile AB and here AC. Another test was where compare the simulated sediment volume with the volume of sediments found in Salgado's drills. And we saw some difference between the real volume of sediments and our simulation. And here we can see a video with one of the simulations. in blue are the deposit, the sediment deposits, and the difference between the dotted line and the continuous line was the erosion. For each one, we gave grades for each one source and results based in this analysis for each one sources. And we put this on a matrix where we can find, we can see higher grades and lower grades. Lower grades means the bad match, and the high grades is a good match between the parameters and the simulations. What we can summarize from this analysis? That the geological resistors could not define the right source, but could help to exclude no consistent sources. That's all.
Thanks a lot, Francisco, and also a word of acknowledgement to Guy, that I think recently retired, and Jean-Paul, that I think it's early morning for him. So thank you all for this great effort that you conducted. So I'll pass it to Ivan and then to Marty, and then we will have some questions regarding the modeling exercises that we made. So thanks a lot, Francisco.
Okay, thank you.
Okay. Think you all can see the presentation? Yeah. Okay. So it's good that Francisco has presented before me, because somehow our presentation complement themselves, and I'm gonna present the results from application of forward and inverse models to tsunami applications. So the main goal of this presentation, I think we can resume to reconstruct historical tsunami events through numerical modeling, but with a link of these results to field data. So I'm going to briefly present two case studies. The first one, it's going to be based on the modeling presentation that Francisco just presented, where we are going to reconstruct the 1755 tsunami and estimate the onshore flow velocities. And the second case study, it's going to be at our margin lowland, which Pedro just presented at the beginning of the presentations. And I'm going to show some modeling exercise that we've developed regarding tsunami overtopping and storm events overtopping in this area. So starting from the first case study, just to briefly resume here, we are going to estimate historical tsunami onshore flow characteristics, namely the 1755. Why? I think evaluate past events to improve other assessment. And how we're going to be done this, we are going to use inverse model and a forward model. Basically, inverse model, we are going to base our results on sediment characteristics, where we estimate tsunami flow behavior based on sediment samples. And we are going to use the forward model results just presented by Francisco, but only the hydrodynamic model results. We are not going to go in depth with the morphodynamic just presented by him. So these are available tools and complementary approaches that very suitable to this kind of work. I already mentioned that we are going to focus on Salgados Lagoon, Algarve, where we have large sedimentary data sets. So just an overview of the general setup of the modeling strategy. So black boxes represent the hydrodynamic modeling areas. And here we have satellite images showing the 4 sediment samples corresponds to Livingston samples that we have collected at Salgados. that it's going to be used for the inverse model calculations. The methods, we divide this work in two methods. The one is the inverse model application, the other one is the forward model application. Basically, the inverse model application is based on the segment analysis, basically high grain size analysis. And we applied the two-segment model by Jaff and Gelferman, where we basically estimate the flow conditions that are needed to put segment into suspension. And that's why in this calculation, we only use the suspended load layer to calculate the tsunami flow velocities. And that's why also it's very important to have good interpretation of this segment stratigraphy and identify the bed load layer and the suspended load layer, obviously the tsunami load layer. And so we're gonna apply this inverse model to estimate the tsunami flow characteristics and compare to the results, hydrodynamic results from forward model based on Delft 3D application. Well, what we could achieve from this comparison, basically, we could we can notice here that the tsunami flow onshore velocities are very similar for both inverse model and forward model, and they are very consistent. And we get similar results, which is very encouraging. Also, we found better results for the Marquês de Pombal fault source simulation, which doesn't mean that this is the source of the tsunami, obviously, but it is in agreement with the work of Francisco that present better results for Marquês de Pombal and scenario one source scenarios. Also, one interesting result that we've got from this is that this onshore flow velocity corresponds to tsunami wave offshore height of 3 meters height at 50 meters depth, which corresponds to approximately a wave height of 8 meters at the coast, which is in agreement with the work of Pedro and Susana Costas that was presented at the beginning of the presentation, showing the erosional features onshore that also constrain this tsunami height at the coast. So the second case study, we are going to evaluate tsunami and storm overtopping events at our margin lowland, also trying to contribute to hazard assessment improvement. And how can we do this is through segmentary records, which is not included in this work, but we also have a complementary approach, which is numerical modeling. It's a useful tool that can give insights on the hydrodynamic behavior and the coastal impacts of those events. Okay, so why we chose our margin lowland? Basically, it presents a complex stratigraphy with the coexistence of storm and tsunami onshore deposit. I think it was already presented by Pedro. Quite overview of the area, where you can see in detail the complex stratigraphy at our margin trench with multiple high energy washover events. At the top, a sequence of storm deposits highlighted by the heavy mineral layers. And at the bottom, the tsunami, the potentially associated to 7055 event. Also, those storm events at the top, we potentially have here registered the 1941 cyclone, which has hit Portugal. I think the major event of this nature ever hit the continent. Okay, so our modeling strategy was for the 7055 tsunami, we used Delft 3D and applied a 3-meter height offshore wave, already based on the previous works performed on the region, which seems a consistent value for the offshore height. We used hydromorphodynamics approach and a cross-shore variable grain size. And for the storm event, we applied a X-beach model. This is an event, we don't have too much information regarding this. We are basing our simulation on the 1941 windstorm. But we could find some information regarding the surge level, which was approximately 70 centimeters, and the wave height and period was based on statistical and return periods, which seems consistent to the event. For now, the simulation is only performed in hydrodynamic mode, and the next step it's going to be apply a morphodynamic approach. So, a resume of the results for the 1955 tsunami. The 3D results show onshore deposits till 500 meters inland, and the inundation reaches approximately 1 kilometer inland. The onshore deposit thickness was around 10 centimeters, and the dune was evaluated as the main source of sediments, which was totally compatible with the field data that we have so far for the region. And regarding the storm simulation, we have some preliminary results with dune overtopping and inundation of approximately 400 meters inland. And the next step, it's going to be the sediment transport modeling. So just some final remarks regarding our numerical modeling results. This was the first time inverse modeling approach was applied to tsunami deposits in Portugal. And some quantitative and valuable information regarding tsunami wave characteristics could be retrieved. We also found good agreement between modeling and field data, and we think we could give some valuable contribution to tsunami hazard assessment. And once again, we can say that we both works at Salgados and our margin lowlands points to offshore wave heights, tsunami offshore wave heights of 3 meters at 50 meters depth and around or over 8 meters at the coast, which matches the field data that in the regional and the position of field onshore data that we have for the area from previous works. So that's it.
So
Thank
thanks
you
a lot, Ivana. Thanks for all your work. Ivana was the main researcher of employed by the project, and she presented some of the results that were quite encouraging because as a geologist, I was always very skeptical regarding some of the models, and I'm more and more convinced nowadays with some of the results because I think they approach what I've been seeing on the field.
Yeah. But we did field data,
and
definitely.
that is good. And now probably Martin will prove me wrong. I don't know. So the next one will be Martin to talk about his work. Martin entered the project at a very late stage, and we all should congratulate him because he finished his PhD very recently. I think a month ago or something, not even that. So congratulations, Martin, and the floor is yours now. Thank you.
Thank you very much. So I'm glad that Francisco and Ivana presented before me, and that I can confirm the values. So this is the good news. And the other good news is that I finished my PhD and that I'm quite happy that it's done now. So I start to share my screen, which I cannot do because the host disabled participant sharing screen. Okay, now it should be. So, okay. So can you see the screen? Yes. Okay, so just quickly about my work. So I started like just a couple of months ago on this topic, and well, the objectives have been set already. So it is trying to reconstruct the tsunami events, and here specifically the 1755 event by combining the sedimentological records with the numerical modeling results. And this is important for the characterization of the coastal hazard and risk associated with these events, especially in this area, because we know that they are not that frequent here, and it is important to evaluate the recurrency rates. And here in this work, I combine numerical modeling and impact evaluation to compare the results with the geological records of the 1755 event in the Northeast Atlantic. And the methods that I use is I considered only two sources, not the full range of sources, but they are slightly different from those that have been proposed. Then I use the coseismic deformation to compute the tsunami wave, coseismic deformation, and then compute the tsunami waveform. I applied the numerical model, and swing, which is a non-shallow water code. I compute the waveforms at the 200-meter isopath that you can see here, and extract the waveforms that are associated to the observation sites on land. First, I apply the Green's law to approximate the nearshore wave heights, and then I evaluate the tsunami impact using one of my methods presented in my PhD, the tsunami run-up predictor. As I've said earlier, I considered two different sources. As earlier has been proposed that the magnitude of the estimated magnitude of the 1755 event, a single structure could hardly explain it. So a couple of authors proposed that eventually subparallel structures could have ruptured together to generate this magnitude. I use here a combination of the Horseshoe plus Marcus Bombard fault, where you can see the deformation, the maximum wave height produced by this event on the right side. And the recent work by Martinez Lariente, such as the Horseshoe abyssal plain thrust fault, the deep-rooted fault, which is presented here at this area, to be a corresponding candidate source for the event. In fact, the locations are quite similar, but these authors propose that the eruption nucleated at greater depth and propagated upwards. Then I compute the coseismic deformation with considering these parameters for each scenario, and put it into the numerical model, propagate it to the 200-meter isopath, and expect the wave shapes in the time domain. Here just a couple of examples. What we can observe here that we have approximately how come a 3-meter wave height and the southern coast of the Algarve at the 200-meter depth contour, and on the western coast it's a bit above 1 meter, decreasing towards the north. I applied the Green's law to the wave height of the first wave, which is basically the wave height at the shore is related to the wave height offshore to the quad root of the depth offshore divided by the depth close to the shore. By knowing the velocity at the 200-meter isopath, I also can convert it, especially the accelerating phase that I find is important for the run-up. I can convert it from the time into the length domain. So considering the tsunami run-up predictor, the accelerating phase of the wave can be described by the parameter LP, which is basically from the trough of the wave to the peak of the wave. And then we extract all the necessary parameters. So we did a subroutine to extract the parameters So we extract the wave height, the amplitude ratio between positive and negative amplitude, the accelerating phase of the wave in the length domain, and d, which is the depth divided by sine beta, which is basically the length of the slope. So, and then we use this formulation to estimate the run-up duration. In this figure, we can just see the approximation of the values. So I just the orange line depicts how I find these parameters to pick for the input of the tsunami run-up. And what we can see, so I computed for, so we had the numerical model that gives the output of the wave height at 200 isopath. And then we had the Green's law computing the wave height at 10 meters, 5 meters, then the expected mean run-up, and then the expected extreme run-up. Here I have one example for Scilly Islands, where we have a sediment deposited peak pool. The offshore wave height of 25 centimeters for both models, more or less similar, located here, is like 25 centimeters. Coming closer to the shore, it grows to half a meter, slightly above half a meter. And the mean expected run-up would be around 3 meters for the Horseshoe abyssal plain thrust and only 0.8 meters for the Horseshoe Marcus Bombal fault. The extreme run-up also varies greatly. The extreme run-up for the Horseshoe abyssal plain thrust would reach nearly 8 meters. Similar exercise for the Tagus estuary. We have approximately 1 meter wave height at 200 meter ethopath, and then the wave is growing close to the shore up to 3 meters, and we would expect run-up values within the Tagus estuary between 3 and 8 meters. And at Salgados, so we have an offshore wave height that is 2.5 to 3 meters, approximately closer to the shore. We would expect the wave height of 6 to 7 meters, producing a mean run-up between 7 and 8 meters that could potentially produce an extreme run-up of 20 to 22 meters. So here I would like to mention that the extreme run-up requires a specific bathymetry. So this is a simple empirical formulation to evaluate the mean run-up. So we consider a 1D profile, and for the extreme run-up, use the field case. But these field cases were limited, and so we have to take these values, the extreme run-up values, with some care. Okay, another important, sorry for the table, it's not very illustrative, but the most important things are the colors. So green basically is like a confirmation of the sediments, and red would demonstrate that there is some disagreement. The blue areas, well, I do not have a estimated height above the mean sea level, so it's hard to compare, but well, this is inside the Tagus estuary, so I'm sure that they are confirmable. What is not in agreement is like some boulder deposits that have been found Cabo Delgado and Cascais, and boulder deposits in Praia do Maranhão. So these boulder blocks should be located 20 meters above the sea level. When we see even the extreme run-up values in this area, we have 4.6 to 5.6 meters. These values cannot explain the deposition of these blocks. And it's similar in Cabo Raso and Cascais, where we have extreme values up to 5 meters. So we cannot expect that the boulders have been deposited by the 1955 tsunami. And here's just a red area because I figured out that there is something, especially if the wave shape is a bit more complex, the parameter extraction needs some further refinement. But this is some methodological aspect. So as concluding remarks, I can say that this method allows us to evaluate quickly the tsunami impact, and it's quickly and reliable validation for deposits. found in the field. The run-up values for the Horseshoe Plain Trust and the Horseshoe Marcus Bombal fault agree with most of the positional features. It seems that the Horseshoe Plain Trust seems to be more effective in the far field. In the field, in the near field, both produce similar run-up values. As I've mentioned before, the waveform extraction method requires some further refinement, and the 3 boulder deposits, Cabo de Raza, Cascais, and Praia do Malhão, were unlikely deposited by the 1755 tsunami. Why unlikely? Because if you consider a different wave shape or a different source, we might reach these values. However, it must be taken, the sources must be chosen with care, and this is why it's important to combine the sedimentological records with the numerical methods. Thank you.
Okay, thank you, Martin, for your talk. We are really late, so I will give you some time for discussion now, and then I'll just need the last 5 minutes to talk a little bit about the dissemination that we conducted and, well, concluding remarks. So I will give like 10 minutes if people want to ask questions now. If not, I'll move to the dissemination bit. So throughout these presentations, we've been talking about onshore erosional, onshore depositional imprints of tsunamis. Then we focus a lot on the peculiarities of the 1755 aspect when we look at the nearshore record, and the fact that we have detected a new event, the 3.4 event, that is of importance when we look at return periods. Regarding the models, I would say that models and geological data are getting closer. They don't fit everywhere, but I think we are getting closer. I still am a bit concerned of the fact that all the models rely on the proposed generation mechanism. Then there is some uncertainty regarding that. But they are good approaches, and if we can validate them and we can work together between using the sedimentological data, that would be very, very important for future works. So if someone has questions, now it's the moment. Otherwise, I'll talk for 5 minutes more, and then I'll probably end the meeting. So I will just would like to say that this is the project ends next week. Okay, Martin. Yes. Boulders are quite complex because with sandy deposits we have stratigraphy, and because the deposits are framed and it's easier. Boulder sediment transport, it's more complicated. There's been some empirical approaches, very interesting ones. Even in Aachen and Cologne, they did a nice experiment on a wave flume. I remember Kazu Goto, the Japanese colleague, did some. I will reply to João in a second. Kazu Goto did an experiment. Well, basically it was an empirical experiment. So they went to the Japanese coast and they measured some boulders, and then there was a big storm and they measured the movement of the boulder. The same has happened in Ireland with a group of American colleagues that have been monitoring the Aran Islands for a long period. And there's now a group that has been created over the last months or so. I think Some of the Italian colleagues that might be here, they attended that meeting with me. So the group is international, is funded by the National Science Foundation of the US. And the idea is to create a network of scientists that look at boulders. And one of the aspects that clearly came out of that meeting is the need to standardize observation. So people measure boulders the same way, they provide the numbers the same way. And of course, the need to further develop numerical models. So that project just started. And that network is created. They are building up a database for the whole world. They are trying to involve as many people as possible. I can share the link if someone asks me. I don't know it by heart, the name of that.
Can I say just one thing to the
yes,
boulder question that have been?
Yes.
So coming back to this boulder issue in Cabo do Raso and Cascais, they are located at the location of 18 meters above sea level. So the wave, the maximum extreme run up, that I could compute is 5 meters. There is no way that this wave reaches that height. I would need to consider a different model, a different source model, and then it would be difficult to reach that height. So I can remember a study that used the the horseshoe fault as a source that produced in Cascais 15 meters maximum, and still it would be not enough to deposit it at this rocky shore. So I believe that the bathymetric conditions there are not given to deposit the boulders at this sea level.
I agree, and I can say that in the case of Cascais, they even mention a 120-ton boulder that was moved, and there's been a lot of work that has been done there. Even recently, we were there using laser scan to measure the boulders properly, and it's really hard to see how they were moved by that. We analyzed that. I think I saw Conceição Freitas is here, and probably Pedro Cunha was also on that campaign. I don't know, 15 years ago, we went to see those boulders, and we could see dynamite holes. So many of the boulders were moved in favor of gravity, against gravity. So the boulders from Cascais it's from the sedimentological point of view, they were also quite intriguing and difficult to explain. So if the models help, and if we can talk together with the model results and with the sedimentological data that has been produced, that would be really good. João asked about the tsunami sedimentation model. I'll talk about that as future work. Let me just go. I don't know if there's more questions. Otherwise, I'll just need to briefly mention. I'm not going to present anything more because I would like to end the meeting at 5. It's been a long session for most of you, and I know that some are quite busy, and I really appreciate that I'm not going to say wasted your time, but that you provided your time to be here and to listen to us. As you can see, although we are getting closer to the end of the project, we have so many things that we could do, and that's a good thing when you have a project. In terms of the dissemination and outreach, we have some goals that we needed to meet. We had 6 papers, and we published the 6 papers. We had several chapters. We have more than 20 presentations on conferences, but more importantly, we had several students. I just had a meeting on Friday with a student that is planning evacuation routes in central Portugal, not only for tsunami, but also for storms. There's a large number of students that have benefited from going to field campaigns. Over the last weekend, 11th, 12th, and 13th, we had some students from the University of Coimbra that went and were able to see how we dig a trench and how we look at the trench in the area of Monte Gordo. So for me, that was quite important. Also, important was that we did around 15 visits to secondary and primary schools. And I was amazed with the enthusiasm that they had, particularly when I told them that Meteor, the boat, was like a 4-star hotel instead of a research vessel. And they were impressed with the karaoke bar and everything that we had on board. And I hope that in I don't know, 15 years time, one of them comes to me and said, well, I decided to go for geology, coastal geology, marine geology, or modeling because I listened to your presentation. So in a way, we try to fulfill that. All our data is available if someone requests it. It's open access for many in many aspects. And that's what I can say regarding outreach. Before I finish, because it's 5 minutes, so regarding future work, Lisa mentioned something that I'm really enthusiastic about, and it will relate with the development of a tsunami sedimentation model. The CT scan images that we got recently are, it's like, I don't know, some of you are too young, others remember when we first had 3D films. And we had to use the glasses that allow us to see a different dimension. And when I look at the CT scan imagery, and according to Rafael, and we have now the most extensive database of tsunami deposits on CT scans, it is really a totally different dimension. The perception that we get for sediment dynamics, the way we can see clasts imbricating, the way we can see shells, it's totally different. It's really adds so much that facilitates to develop a tsunami sedimentation model, even if it's of local relevance. And to finish, I have to say thank you, all of you that are here, all of you that somehow contributed to the project, being part of the team or not. And I have to say many thanks to all the colleagues that through these 3.5 years, I was fed up of the project towards the end. But through these 3.5 years, it's been a very productive project, and for me, scientifically, it's been great working with you and learning so much. And I hope we continue doing this. I have to a special word to Ivana, to Lisa, that have been key persons in this project. I'm sure they will have success in their academic future. And it's been a privilege to work with you all. In terms of science, I think we have a new return period for tsunami events in Portugal. We have a new perception on the tsunami sediment imprints and its dynamics and how they behave. And I think models are getting closer to reality. They are always an approach to reality, but what I see on the sediments, I can now relate quite easily with the models. So after 3.5 years, I'm quite happy with all this progress that was achieved. Tsunami geoscience started with Atwater 87, Dawson 88, Andrade 91. There's plenty of things to discover. I will try to focus on floods now, if I have the opportunity to study floods. But it's been a privilege to work with you all, and I wish you all the best and thank you, okay? So I'll now stop recording, and if anyone has any question, you have 1 minute. Thank you.